Hello, I welcome you all in this presentation. This presentation is based on the solidification cracking and its control. You know that this type of cracking is observed mainly in the weld metal, and especially in case of the base metal having the wider solidification temperature range, or the impurities are involved too much in the base metal leading to the wider solidification temperature range, or inappropriate selection of the base metal is made leading to the wider solidification range. So, these are the some in all these cases the common factor is the solidification temperature range which is observed. If it is very wide, then it promotes the solidification cracking, and it can occur not necessarily only in the aluminum alloys, but also in the stainless steel. It is observed especially when the silicates of the low melting point are present in the stainless steel, or impurities like sulfur and phosphorus are present in the large quantity. So, all those factors which are promoting to the wider solidification temperature range, increasing the residual stresses, they will be causing the solidification cracking. So, solidification cracking is basically the weld metal cracking, and invariably it occurs at the center line of the weld. It occurs at the last stage of the weld solidification. So, last stage of the weld metal solidification. So, we will try to understand these are the common things. Occurs at the center line of the weld, it occurs in the weld metal, and invariably occurs at the last stage of the solidification of the weld metal. So, now we will see first the mechanism or the way by which it happens. Like say this is the plate welded, this is the center line, and the weld made along the center line is like this. So, if the solidification temperature range is really very wide for this metal, which may be either autogeneous or the filler is added, resulting in the wider solidification temperature range. In both the cases, we can find the crack running all along the weld. So, maybe crack may run like this all along the weld. This is called solidification crack. So, how does it happen and how does it start? We know that whenever the two plates to be welded like this, when they are fused with the application of the heat like this, so one fusion boundary is there, and we will be having the along the fusion boundary we will be having the partially melted grains. So, solidification starts basically from the fusion boundary. In epitaxial solidification, typically this is the it starts with the planar solidification, which is almost pure metal most of the time, and then it will have the cellular structure like this. So, solidification proceeds by consuming the liquid metal, and the impurities or alloying elements are rejected into the weld metal. So, after the cellular structure we have the dendrites like this. The dendrites also grow by consuming the liquid metal and rejecting the alloying elements and impurities in the weld metal. So, this is how things will be growing from both the sides. So, similarly the planar other side also cellular and then dendritic like this, and at the end what we have, equaxed dendritic at the center. So finally things left for rejection at the center. So finally actually the solid liquid front proceeds from the fusion boundary towards the center line, and towards the center line, towards the center of the weld. And so whatever is the molten metal left at the center, so molten metal left at the center, this has a large amount of like impurities which were rejected in course of the solidification, or the alloying elements. So impurities like sulfur, phosphorus, lead, or alloying elements like copper, silicon, manganese, etc. So there is a continuous change in composition of the liquid weld metal during the solidification of the weld metal, and what we have at the end is enriched with the alloying elements or the impurities. So we know that as the alloying concentration increases, as the impurity concentration increases in the in any metal, its melting point decreases. So high concentration of the alloying elements and impurities results in the reduction in the melting point or the solidus temperature, or the temperature at which it will be solidifying. So this reduction leads to the situation where entire weld metal has already got solidified, but it is still there is a liquid metal which is present along the at the center of the weld. So the base metal which was heated to the different temperature values during the welding, and the weld metal which was brought to the molten state in course of the cooling regime of the weld thermal cycle, all these things start shrinking, and shrinking under the restraint conditions results in the residual stresses. So shrinkage in the heat affected zone and shrinkage in the weld metal, all these results in the setting of the tensile residual stresses. And tensile residual stresses, all these residual stresses will be localized in the center where we have the liquid metal. Since the liquid metal actually cannot support these residual stresses, so it gets separated. So this separation ultimately happens in form of separation of the equaxed or the dendrites at the center, and it leaves a gap between these two, especially at the center line, which in turn appears in form of the solidification cracking or solidification crack. So if we see, this occurs in the very last stage of the solidification, and especially when the impurity concentration is high or a lot of alloying elements are left at the center, and this typically happens when the alloying elements are present in the large quantity, or a very present in the very small quantity, or then this kind of the cracking is invariably observed. So for a particular kind of composition of the aluminum or of the any metal where where the low melting point liquid metal is formed in very limited quantity, then only the solidification cracking occurs. If the low melting point liquid metal is formed in large quantity, then all the separation of the separation due to the tensile residual stresses is filled in by the presence of the liquid metal present in the large quantity. So in the two situations, when either the metal is pure, then the entire solidification will be taking place at one temperature, and there will be no rejection of the impurities or the low alloying element in case of the pure aluminum or the pure iron. Similarly, in case of the eutectic systems also, melt and solidify at one temperature. So they will also be solidifying or melting at one temperature. So there is nothing like rejection or rejection of the impurities and the alloying element. So especially in the cases where the concentration, where the amount of the liquid metal being formed at the last stage of the solidification is very limited. So this limited quantity of the liquid metal is found insufficient for healing the cracks which are being developed due to the tensile residual stresses at the center line of the weld, and this in turn leads to the development of crack. So this is what is called a typical solidification cracking. So there are few contributors for the solidification cracking, and these contributors can be categorized in two broad groups. One is the metallurgical factors and another is, we can say, the mechanical factors. Among the metallurgical factors, the first one is the factors alloying, affecting the solidification temperature range. So the presence of the certain alloying elements increase the solidification temperature range significantly, and they in turn leads to the increase in the solidification cracking. Then the amount of the low melting point, the liquid metal. So if the amount of the liquid metal is either absent or it is very negligible, then there is no solidification cracking, or if its amount is very large, then again no solidification cracking is observed. For a very little quantity of the low melting point liquid metal present at the center line of the weld, this particularly increases the cracking tendency to the maximum level. Next is the distribution, how the low melting point liquid metal gets distributed. If the low melting point liquid metal forms the film, then it becomes most crack sensitive, and if it forms the spherical inclusions or it forms the ball shape and it is present in very localized form, then it reduces the cracking tendency. So distribution in form of films or layers, this promotes the cracking maximum, and like iron sulfide forms the films of the iron sulfide and distributes along the grain boundary, that promotes the cracking significantly. Then the grain orientation during the solidification, the grains can grow perpendicular like this, or they can grow in curved columnar form. So the columnar grains having the high or steep abutting angle, they promote the cracking tendency due to the increased low melting point alloying due to the increased tendency of the segregation of the alloying elements or impurities along the weld center line. So the grain orientation is one of the factors. So the curved grains, they lower the solidification cracking, while the abutting high steep the grains growing perpendicular to the fusion boundary and abutting at a high angle at the center, these promote the concentration of the alloying element at the center line, and so they promote the solidification cracking. Further, the grain size of the whatever is being formed. So finer grains in turn results in the large grain boundary area, reduces the concentration of the low melting point liquid as compared to the coarse grains. Coarse grains promotes the cracking, solidification cracking tendency as compared to the fine grains. So another is the mechanical factor. Under the mechanical factor, we have like the factors which are related with the residual stresses. So residual stresses, for example, all those factors which promote the tensile residual stresses, they will be increasing the cracking tendency, while other factors Similarly, the factors which promote the residual stresses, like the joint design, determining the volume of the weld metal, then composition of the filler, like yield strength of the weld metal, composition of the filler, determining the yield strength of the filler metal. Higher is the yield strength, greater will be the residual stresses as compared to the low strength filler metal. Similarly, the bead weld bead geometry, concave beads, concave bead and convex bead. These are the two types of the beads which can be developed. So, the concave bead promotes the compressive residual stresses, while the convex bead promotes the compressive residual stresses and residual stresses, and while the concave bead promotes the tensile residual stresses. So, tensile residual stress, this will be promoting more cracking tendency at the center line as compared to the another one. Likewise, there are another factor is the restraint. Higher is the restraint during the welding, greater will be the residual stresses. Apart from that, the composition of the base metal or the filler metal which is being used. So, all these factors will be discussing at length to show how these factors affect the solidification cracking, and these factors itself will give us idea about what can be done in order to avoid or in order to reduce the solidification cracking tendency. For this, we will be going through the certain diagrams. So, typical diagram which it shows the crack running all along the center line of the weld. This is the typical diagram showing the solidification cracking, and it is the interdendritic. Whenever the fracture surface the cracked surface is cracked mouth is opened, then you will see that the separation is there between the dendrites, and the typical the morphology of the fracture surface on separation shows the presence of the dendrites, because it will be developed because this kind of the separation happens when the gap is not filled in by the liquid metal, especially when its amount is very limited. So, the factors as I have explained, and there are two categories of the factors that affect the solidification cracking. One is the metallurgical factor, and most of these metallurgical factor will be actually influenced by the segregation tendency. So, solidification temperature range, if the alloying elements are more or less, so that will determine the solidification temperature range, because as the solidification proceeds, more alloying elements are rejected. So, that in turn will be affecting or determining the gap between the liquidus and the solidus. Amount and distribution of the liquid metal at the last stage of the solidification, like if the amount is very less or amount is very large, in both the cases solidification cracking will not be happening. But if the amount of the low melting point liquid metal left at the last stage of solidification is in between, then it will promote the cracking to the maximum level. And similarly, the distribution if it is present in form of the film, then it promotes the cracking as compared to the case when the liquid metal is present in form of the like balls. So, primary solidification phase, especially in case of the steels, if the solidification starts with the austenite, then it promotes the cracking, because in presence of the sulfur and phosphorus, these increase the solidification temperature range significantly, while in case when those steels when the steels solidify with the delta ferrite as a primary phase, means on the solidification, first of all the delta ferrite is formed, then in that case the impurities are absorbed by the delta ferrite, because these act as a sink for the sulfur and phosphorus, having the much larger the solubility for the sulfur and phosphorus. That is why the formation of the delta ferrite as a primary phase reduces the cracking tendency as compared to the case when the austenite is the primary phase in case of the steels or stainless steels. Then the surface tension, if the surface tension is less, then it will form films, and the films and layers of the low melting point things will be promoting the solidification cracking as compared to the high surface tension the liquid metal which will be forming the balls, and it will be present in very localized manner. Then the grain structure, finer grain structure and the columnar grains, the columnar curved grains, the finer grain structure and the columnar curved grains reduce the solidification cracking tendency, because these increase the distribution of the low melting point phases, and that is why it lowers the solidification cracking tendency. So, all these factors are either directly or indirectly affected by the weld metal composition, and since in course of the solidification there is a continuous rejection of the alloying elements, that is why there is a continuous change in composition of the weld metal, and that is why microsegregation also results in sometimes the form results in the solidification cracking due to the rejection of the alloying elements. So, microsegregation in turn can also microsegregation affects the composition of the weld metal, and microsegregation can is actually influenced by the cooling rate. If the cooling rate is very high, then we do not get means liquid metal does not get much time for rejection of the alloying elements, and in that case we get much more homogeneity and uniformity in composition as compared to the case when lot of time is available for rejection, especially under the low cooling rate conditions. So, the microsegregation tendency will be much higher under the low cooling rate conditions, and which will promote the solidification cracking. So, as far as the factors that will be affecting the solidification temperature range. So, if we see here the weight percentage of the different alloying elements like silicon, carbon, phosphorus, sulfur and boron, and how do these elements affect the solidification temperature range, especially in case of the iron. So, freezing temperature range 100, 200, 300. So, if we see here the very little addition of the sulfur results in the maximum increase in the solidification temperature range of about 150, and the boron, similarly the addition of the boron increases the solidification temperature range by 100 degree centigrade, and addition of the phosphorus of about 3% results in the increase in solidification temperature range or the freezing range by more than 300 degree centigrade. Similarly, carbon also increases the solidification temperature range of freezing range, and silicon, although however the effect of the silicon is less as compared to that of carbon, boron, phosphorus and sulfur. When there is no, so now we will see that when the system is pure, there is no range, so there is no grain boundary liquid metal, and when the silicon when the elements like only silicon are present, the range is very narrow. So, very little amount of the liquid metal will be present at the grain boundary, but when large amount of the when the sulfur, phosphorus or the boron, when these are present in the large quantity, they will be resulting in a very large freezing range or solidification temperature range, and this in turn will be leading to the presence of the large amount of the liquid metal at the grain boundary. So, this thin layer of the iron sulfide which actually sulfur will be reacting with the iron and forming the iron sulfide in form of thin film along the grain boundary. So, now coming to the aluminum, as I have told that very less amount of the sulfur, very less amount of the liquid metal does not cause the solidification cracking. Similarly, very large amount of the liquid metal also does not cause the cracking. That is what we can see here. The aluminum with 0.1% copper having very limited quantity of the liquid metal, which is not sufficient to promote the cracks, while similarly in case when the very large quantity of the liquid metal is present with the aluminum 8.4% of the copper, then it promotes then also whatever cracks are formed, they will be filled in by the low melting point liquid metal present in the large quantity. But when the case is in between, like aluminum 4% copper having the limited quantity of the liquid metal, so this will promote the cracking, and when the cracking is occurring to such an extent that the developing cracks cannot be filled in by the limited quantity of the liquid metal which is present. That is why solidification cracking tendency or crack length is very limited up to 1%, and crack length further reduces with the copper content more than 6 or 7%, and the crack length is maximum for about 4%. So, the same trend we can see for the other aluminum alloys, like for the crack sensitivity for the solidification cracking as a function of the different alloying elements. What we can see here, silicon with about 1% results in the maximum cracking tendency. It is less with the less cracking tendency is less with very limited quantity of the silicon as well as higher quantity of the silicon. Similarly, the copper for about 4% it results in the maximum cracking tendency. About for 1% of the magnesium it results in the maximum cracking tendency, and for higher concentration of the magnesium, copper and silicon, this cracking tendency keeps on decreasing. So, now coming to the relative amount of the phases, when the relative amount is very less, like there is no liquid metal present at the grain boundary, so cracking tendency is very limited. But when very thin layer is present, the cracking tendency is maximum, because it just gets separated and then separated crack is not filled in by the limited quantity of the liquid metal. On the other hand, when more solute is there, the increased amount of the low melting point phases, it reduces the cracking tendency, because whatever crack is being developed, it will be filled in by the already existing low melting point metal, and when it is present in the large amount, then the cracking tendency is further reduced. So, for very less amount of the liquid metal and for very large amount of the liquid metal, cracking tendency is very negligible, while the cracking tendency is found maximum when it is present in very limited quantity, but is forming the thin network along the grain boundary. Now, coming to the primary solidification phase, especially this is true in case of the stainless steel. When stainless steels can solidify either as a austenite as a primary phase or the ferrite. When the ferrite is formed as a primary phase, we find that there is no cracking tendency. Primary phase formation is when primary phase is ferrite, the cracking tendency is negligible or no cracking tendency, but when the primary phase is austenite, it results in the maximum cracking tendency. So, whether there will be a primary phase ferrite or the austenite, that is governed by the undercooling experienced during the welding, and even for the given chromium nickel equivalent ratio, chromium and the nickel equivalent ratios, what we can see this happens, like for the laser welded joints, the chromium to the nickel equivalent ratio more than 1.7 results in the primary ferrite phase formation, while less than 1.6 chromium nickel equivalent ratio results in the primary austenite phase formation, and this ratio is found between 1.4 to the 1.6 in case of the arc welded joints. So, conditions are developed in such a way that our primary phase is ferrite, so that it can reduce the cracking tendency. Why the ferrite formation? Why formation of the primary ferrite lowers the cracking tendency? That is what we can see from this diagram, that ferrite has a higher solubility for the sulfur and phosphorus, that is 0.18 and 2.8 as compared to the austenite. Solubility of these impurities for austenite is very negligible. So, the ferrite acts as a sink for these impurities, and therefore, it absorbs all these impurities and lower the cracking tendency. That is what we have seen. So, surface tension also affects surface tension of the liquid metal lost to solidify, also determines the cracking tendency in one way when it is of and this is measured in terms of the dihedral angle. When dihedral angle is very less, then we will see the cracking tendency is the dihedral angle is 0, then we will see that the liquid metal forms a continuous film along the grain boundary and the cracking tendency is very high. When the dihedral angle is high, then it forms like nodules or the globular or ball shape. So, this kind of structure will be reducing the cracking tendency as compared to the case when it forms thin film. So, this is what can be seen schematically here. When it when the low melting point liquid forms a continuous grain boundary film, then it results in the maximum cracking tendency, while in case when it forms the balls or discrete nodules here and there, then it reduces the cracking tendency. So, especially like the addition of the magnesium in the steels forms the magnesium sulphide instead of the iron sulphide, and magnesium sulphide is present in form of the nodules or the balls, and further it has the higher melting point. So, as compared to the iron sulphide, so it reduces the solidification temperature range, and whatever nodules are there, they are present in the form of the balls, not in form of the network, and therefore it reduces the magnesium addition, reduces the cracking tendency. Similarly, the grain size concept, when the grains are fine, then cracking tendency is less because low melting point things are well distributed and the concentration of the low melting point things is less, low melting point metal along the grain boundary is less. When the grains are coarse, there will be very fewer grains, so fewer grains will have the higher concentration of the low melting point liquid metal along the grain boundary, which in turn will promote the cracking tendency. Similarly, when the grains having the high abutting angle, they meet at the center, so this will be causing the localization of all impurities and low melting point things at the grain boundary, and that is why it will be promoting the cracking tendency as compared to the case when the grains grow in curved columnar manner, which will be leading to the very scattered distribution of the low melting point liquid metal along the weld center line, and so it will be reducing the cracking tendency. So, the among the mechanical factors, there are two types of mechanical factors. One is degree of restraint, higher is the degree of restraint, greater will be the residual stresses, and the contraction stresses. Higher is the contraction, so higher is the solidification temperature range, greater will be the contraction stresses which will be set in, higher is the expansion coefficients, greater will be the residual magnitude which will be set in. Apart from the other factors, these also affect the solidification cracking tendency. So, reducing the restraint by reducing the restraint, increasing the preheat and reducing the heat input, these factors in totality will be reducing the residual stress magnitude. So, they will reduce the solidification cracking. A favorable weld geometry, it is better to have the convex bead geometry as compared to the concave, so that the cracking tendency can be reduced as I have explained. Having the finer grain structures either through the inoculation by adding the titanium, vanadium or zirconium, or through the magnetic arc oscillations, grains can be refined. So, the distribution of the low melting point things can be improved and the cracking tendency can be reduced. Then the controlling the weld metal composition, as I have said, filler metal composition is selected in such a way that solidification temperature range is reduced, so the cracking tendency can be reduced. And similarly, dilution also, considering the composition of the weld metal, the dilution need to be controlled as per the requirement. For example, use of the filler in case of the groove weld, when the filler is used, its contribution is just 20% and the base metal contributes to the 80%, while in case of the fillet weld, 80% of the filler metal and 20% of the base metal forms the weld metal, while in case of the groove welds, 60% of the filler metal and 40% of the weld metal. So, 40% of the base metal. So, these proximate contributions should be kept in mind while identifying the composition of the weld metal or selecting the filler metal in such a way that the solidification temperature range of the weld metal can be reduced in order to reduce the solidification cracking tendency. So, now I will summarize this presentation. In this presentation we have talked about the mechanism leading to the solidification cracking and the different factors that will be affecting to the solidification cracking tendency, as well as also I have talked about the methods which can be used for reducing the solidification cracking tendency. Thank you for your attention.